All right. So in this video clip, we're going to be just going through the SN2 mechanism specifically, all right, just on its own. So I'm going to use this simple reaction here. So let's use this reaction. All right, so we're going to have a bromomethane, right, reacting under basic conditions. Generally, they're going to be reacting with hydroxide. All right, so hydroxide anion, and what we're going to be producing is a methanol, which is primary, plus a bromide ion. All right, now to make this a little bit more complex, or well, it's not going to be that much more complex. I could have placed this as sodium hydroxide, right, and then placed this as sodium bromide, right? So yeah, so I might just do that actually. So let's show an entire complete set. All right, so let's do that then. All right, so plus NaOH, and that would give us CH3OH plus NaBr. All right, wonderful reaction. So this is the reaction, but let's look at the mechanism specifically. All right, now we understand that the mechanism of the SN2 reaction, the bimolecular, right, nucleophilic substitution, right, is all about the fact that it's concerted, right? So it is a concerted type of reaction. So it only has one step. All right, you're going to have a backside attack. That's important, and we're going to be looking at what that means. And this backside attack causes inversion of the molecule. All right, if we don't have if we don't have backside attack, we're going to have a front side attack. And the main difference between front side and back side attack is that it can actually produce different types of enantiomers, right? So you can produce different isomers. So let's just have a look at the general backside attack that we're going to be looking at in kit chemistry. All right, so let's draw out this molecule real quick. So let's look at it like this. Okay, so let me actually have this protruding out. All right, and then we have a hydrogen here, and then we have this here, the bromine here. So we have hydrogens in all these places. All right, now what we're looking at is the polarity of this bond per se. So we know for a nucleophilic attack, we must have a generally negative nucleophile. In this case, it's negative, right? Nucleophile, right? That is attracted to a positive charge, or a partial positive charge. So in this case, now the partial positive charge will be created along this bond here, right? Bromine is a halogen, so it's more electronegative than carbon by far. So the electrons in this bond will move a little bit closer to bromine rather, because bromine has a higher electronegativity, which means it has a high tendency of attracting electrons towards itself. So it's going to gain this slightly negative charge, and the carbon here is going to gain this slightly positive charge. And this slightly positive charge is what's going to open up for, a nucleophilic attack, right? And it's going to be a backside attack in this way, right? Why is it a backside attack? All right, the way in which I really look at backside attacks, different from front side attacks, is that it attacks generally in the location where this hydrogen is, pushing to the back, because as we know, the hashed lines means that the hydrogen is located to the back, right? So we're gonna have that type of interaction here, right? A full arrow, because we know that we're showing the movement of 2 electrons, right? And this will actually cause heterolytic cleavage. Heterolytic cleavage means that both electrons in the bond go to one species, and this will occur because bromine has a higher electronegativity, right? So we're gonna have this. Now, a lot of persons, probably would remove the bromine to form a carbocation and then add the nucleophile in this case, which is hydroxide. All right. But this is not how it works. And before I just go along, the hydroxide is generally from this reaction, right? That produces sodium ion plus the hydroxide anion. All right, so that the hydroxide anion is the nucleophile here because it's negatively charged, right? And that's what we have here. Now, this reaction is concerted. This means that it only occurs in one step, right? But we show like 3 different parts, right? Let's call this part A. We're showing the polarity in the bond, the polarization of the bond, attracting the nucleophile in. The second part, let's call it part B, we're going to be showing the transition states, right? So we're going to have something like this occurring, right? So we're going to have something like this occurring. Draw this wedge out. Oh, the wedge disappeared. Draw this wedge out. All right, draw that hashed line out like that. Hydrogen down here. Now what's gonna happen here is that because the carbocation's intermediate is going to be so unstable, it's not gonna wanna actually form that type of intermediate. So we're gonna have, for the sake of stability, a leaving group and an arriving group at the same time. So what this is basically explaining, all right, is that the hydroxyl group is coming in at the same time the bromide group is going out. So this is what the concerted type kind of means. It has the formation of this transition state. All right, so that's what it generally means. So we're gonna have this, okay? And after this transition state, I'm probably gonna have to draw it downwards. After this transition state, we're going to have our actual, molecule now, right? Our product. So we're gonna have inversion of the molecule. So like this, in this case, in this molecule, we know that hydrogens are over in this direction, right? They are pushed in this direction generally, right? It doesn't really look like that right now. Let me see if I can probably move this hydrogen a little bit more over, right? But you understand that the hydrogens are pushed in like that general direction, right? What's gonna happen now is that those hydrogens are moving this direction, all right? So let's have a look. We're gonna have carbon, our hydrogens. So see how the hydrogens move into this direction. Right. So we have that hydrogen here, and we're gonna have that new hydroxyl bond there, creating a primary alcohol. Well, is it a primary alcohol? No, it's just methanol. Because it's not that it's connected to another alkyl group, so it's like that. So it's what we call a type of umbrella flipped, right? So it's flipped inside out. So in the beginning, we had the molecule looking like this. Sorry for my wedges, guys. Molecule looking like this, right? And we end up flipping. So it's like the hydrogen started over on this side, and now they end up at this side of the molecule. So that's the inversion that we're talking about, right? So it's something like that. So we have that there, and we now know that within our solution, right, we have given out the bromide ion. All right, so let me just draw all my electrons, showing that it's nucleophilic in nature, but we still have that one sodium anion out there, right? So those two will react, right, to give us sodium bromide, right? So that's what we have there. So that is generally a summed up version of just the SN2 reaction that we look at in CAPE Unit 2. So we have the reaction, our mechanism is there, SN2, so it's bimolecular nucleophilic substitution of a second order. And we have it being a concerted reaction. It's going to be a backside attack and it's going to result in inversion, right? So part A is just showing the polarity in the bond and the incoming group, the incoming nucleophilic attraction, right? Part B is showing the transition state of the molecule. And let's say that part C is really just showing our product with inversion, and probably this down here. If you have like other ions, like if you had sodium hydroxide, to show that that cation now combines the bromide anion to provide us with a final salt, right? So final product, right? So that's basically it. Thanks for watching.